So I want to take a moment to explain how we made this shift from our komatiite crust to our ocean and our continental crust, because this is actually a really important subject, because this is going to show us a very important mechanism that has started on the Earth. So let's talk here for a second about our komatiite crust. So remember, our komatiite crust is very high in iron and very high in magnesium. And that's why if you look on the previous slide, or the previous couple of slides, you'll see that the komatiite crust is actually green, and it's green due to all the magnesium. Now what's interesting about that komatiite crust is it only forms at 1100 degrees Celsius. So that tells us Earth's surface way back in the Hadean, hot. It was awful, right? Worse than Louisiana hot. So how do we go from this switch? Check this out. To me, this is some of the most amazing stuff, and this is where I'm going to start getting too excited, so you're going to have to bear with me. So here we are, we have these komatiite crusts. We have these plates. And we know, right, due to plate tectonics, that these plates are moving around, right? We've got convection currents pushing them, right, all around, right? So they're moving. And they're moving at a faster rate because they're very, very thin. Remember, the Earth only gets thicker as it cools through time. So eventually what's going to happen is we might have two of these komatiite plates that are going to, let's say, collide with each other. Now let's think back to chapter 7. We learned that when two oceanic plates collide with each other, because they are very heavy, right, and very dense, right, those ocean plates subduct. Well, now we have a komatiite plate that's even more dense than the ocean crust. So what do you think that komatiite plate's going to do? Hopefully in unison you all said subduct. And that's what we're going to see here. So what's going to happen is as one of these plates collides with the other, we're going to have subduction occur. Right? So we've got our komatiite plate here and our komatiite plate here, and it's going to start to subduct. Now let's think back to what we learned in chapter 7. Remember, this is not a friendly interaction right here. Right? Due to the friction, right, from these two plates rubbing on each other, we create a lot of heat. That heat is going to melt the top portion of this downgoing plate. So again, before we go any further, I want to reiterate what's in the komatiite plate. We have iron, we have magnesium, and we will have some silica and some oxygen. Remember, we learned about these. Iron and magnesium love each other and they always stay together, and silica and oxygen love each other and they always stay together. So let's think about this. If we're going to melt the top portion of this downgoing plate, which of these elements is going to melt first? Well, let's think about this. You probably don't know much about magnesium, but you know a lot about iron. Iron is very dense. If I was going to put a piece of iron in my oven, could I melt it? Hopefully you said no. These have very high melting points. They need a lot of temperature. Now let's think about oxygen. Well, we can think about silica and oxygen together, actually. Silica and oxygen together make glass. So, could I put glass in an oven and melt it? Sure enough, I could. This has a very low melting point. So, out of these two things, if I'm going to melt something, what am I going to melt? Hopefully you all said the silica and the oxygen. So, I'm going to melt very felsic material. So what's going to happen is all of that magma is going to come off here, it's going to melt, and it's going to eventually, right, come out of a volcano, okay? And maybe we're going to get some lava flow sitting here on the surface. But what's going to make it unique is this lava flow is going to be felsic. Now, the komatiite crust, this is ultra mafic. So here we have a switch. We are going from very dense, very heavy, to now very light. So, let's think about our difference between our ocean and our continental crust. With this outpouring of felsic lava, which crust am I going to make? Hopefully you all said continent. So, this is making our continental crust. Well, now how do we make ocean crust? All right. So, if we have two komatiite plates that are going to collide, That means somewhere else we have two komatiite plates that are moving away from each other. And remember from Chapter 7 you learned when plates move away from each other we have a divergent boundary. That means all this material that's convecting down here in the asthenosphere is going to come upwards and fill in this gap and make that ophiolite sequence that we talked about. Now, this material is still going to be mafic, but it's not ultra mafic like the komatiite crust is. So if I have just mafic crust, what have I made? Ocean crust. So you might say, well, why is this important, right? In seeing both how the continental crust is made and how the ocean crust is made, this tells us that plate tectonics is in full swing. So by the time we see that shift from komatiite to continent and ocean, we know this very important player is starting to make our planet much more like it is today. So that's why understanding that switch is actually really important, because it tells us something more than just what we can see in the rocks locally in one area and why we see that. It's telling us there's a process happening all the way around the world.